So in the previous lesson, I talked about how to determine the rate law for a reaction if the first step is the rate determining step, is the slow step. And so I want to review this concept really quickly and why we use the slow step in writing our rate law. So I'm going to use an analogy. Here you've got cars and you've got toll plazas. Now, if you think about it, if toll plaza A is the rate determining step, what that means is that because the teller is so slow, it dictates how quickly cars will be able to get through to point 3. It dictates the amount of traffic. Now, in contrast, if toll plaza B is the rate determining step, then what that means is that toll plaza A, cars can just speed through toll plaza A, so it doesn't dictate how many cars can get through to point 3. Instead, it's toll plaza B. And so this analogy is important because just like toll plazas, whichever reaction, whichever elementary step in your reaction mechanism is the slow one, that's going to determine the rate at which your reaction proceeds. And therefore, that elementary step is the step that should be used in determining the rate law. So in the previous lesson, it was really easy because your rate determining step was the first one, and so you simply wrote out the rate law based on the stoichiometry, and there was your answer. Now the issue arises when your initial step is fast and not slow, and this is why. Let's look at an example. So in this example, as you can notice, your slow step is going to be step 2. And so what ultimately happens is there's a backup, because imagine that these are 3 different toll plazas. Because toll plaza 2 is so much slower, you're going to end up with a backup at toll plaza 1. And this is actually going to be helpful for us in determining your rate law. And so what we're going to assume is that at step 1, even though it's fast, because there's a backup, because step 2 is so slow, step 1 is going to exist in equilibrium. Remember, at equilibrium, the rate of your forward reaction equals the rate of your reverse reaction. And so we're going to use this. Now, here's where the issue lies. Based on what you learned in the previous lesson, what you should be able to do is simply take step 2, that elementary step, and use its molecularity in order to determine its rate law, meaning rate equals K times the concentration of X times the concentration of B. Well, what you should notice is that X is actually an intermediate, and you cannot use an intermediate in your final rate law. And so what we're going to need to do is use the fact that step 1 is in equilibrium to our advantage. So let's look at these steps. The first thing you got to do is look at the step before the slow step, and you're going to write the rate law for both the forward and the reverse reactions, and you're going to set them equal to each other. And that's because they're in equilibrium. So for step 1, it would be the rate for the forward reaction would be K, your rate constant, times the concentration of A squared. And I'm going to set that equal to the rate of the reverse reaction, which would be K2, for example, times the concentration of X, because in the reverse, X would be your reactant. Now I can isolate my intermediate, and the way I can do that is simply dividing both sides by K2. So what you would have would be K1 divided by K2 times the concentration of A squared. Well, here's a cool thing. Since I don't actually know my rate constant yet, I can simply say K1 divided by K2 is just K. And so what I get is that X equals K times A squared, the concentration of A squared. Now I can take that value and plug it in for X. And so as I had said before, the rate for this second step, for the slow step, would be rate equals my K times my concentration of X times my concentration of B. And so what I can do is I can simply take my concentration of X that I got in step 2 and plug that in for the X in the rate law. And so what I end up getting is that my rate equals K, because K times K is just K, times the concentration of A squared times the concentration of B. And that, as you notice at the very top, is the rate law that was given to you. So you were able to use stoichiometry and these elementary steps in order to determine your rate law